Welcome back to your favorite engineering mechanics class, for which we are now continuing into our new topic, internal forces. So far you have learned how to calculate support reactions for rigid bodies, and you may think of those support reactions as actually external forces. And today my goal is to talk about internal forces for rigid bodies. So let's understand today what internal forces are. And to help you with that, my goals today are first to introduce internal forces to you. And while I will do that first with a 3D understanding, we will ultimately only look at these from a 2D perspective. That's already challenging enough, and we will have enough fun with that. And we will continue with 2D analyses, but we need to have a 3D understanding of the force system that we actually collapse into a 2D system so that we really understand what internal forces are and, for example, why they are named the way they are named. And that will directly lead us into the proper sign convention that we need to understand and always need to follow to clearly understand how these internal forces work in the 2D world and technically also in the 3D world, but again, that's beyond the scope of this class. Ultimately, we want to be able to really calculate internal forces at any point, but in today's lecture, as an introduction, we're going to do that at a very specific location only. And we do that along the axis of a beam, and today for simply supported beams, just because it's a nice introduction. Later on, our goal will be to not do it just for simply supported beams, but to do it for any type of rigid body and also anywhere along the rigid body. So with that said, let's go ahead and start the lecture, and let's first understand that these internal forces that we are talking about today are really forces that act inside structural members, right? So forces that act inside structural members. And effectively, that means that this is the force that keeps the rigid body together, or the structural member. So it's the force inside that keeps everything together. You may think of this as the glue that holds everything together inside a particular rigid beam. And to further look at that, let's take a look at this three-dimensional picture here of my, let's call it a tabletop. And so I need supports. Let's say I have a support here on the left side, and let's say that's a roller, and then one here on the right side. And let me first spend some time talking about something you have seen and used a lot before, and that is the reference fiber here. In fact, let's make clear that we understand that this thing here is called the reference fiber. Reference fiber. And so far, it's absolutely okay if you just have used it and you didn't care about what it was, but I will explain today to you why you need to understand the meaning of the reference fiber. So from now on, you need to have a clear understanding what the reference fiber does, and you will learn that it actually is related to the definition of the individual internal forces, but more on that later. For now, let's understand and remember that the reference fiber really indicates where the positive x-axis is pointing, and probably more important so, where the positive y-axis is pointing, and that is always opposite to the reference fiber. And you may think now, why do I need a reference fiber? I clearly understand that if I have a horizontal member here, that the x-axis is pointing to the right and the y-axis is pointing up. And that's absolutely correct. But what happens if you deal with a vertical member? Do you put the reference fiber on the left side or on the right side? Or what happens if you have a sloped member that is neither horizontal nor vertical? Then where do you put the positive, where do you put the negative side? So the reference fiber helps us to understand in which direction the y-axis is pointing relative to a local coordinate system that is defined by the axis, in this case the x-axis, of the beam. And you will see when I talk about the specific internal forces how important that is. But now to get to that point, what internal forces are, let's think about the fact that these internal forces are really the glue that keeps the thing together. And what do engineers do when they want to find forces? They pretend that the force is not there. So in the context of this table here, what I can do is I can just cut it, in this case, in 3 individual pieces. And let's just pretend I do it this way. And then when I separate them, what I did, I actually released forces that are inherent to the system when the rigid member is connected. So when this rigid member here is connected, and then you think of this line as the glue line, if you will, then you have internal forces that are connected from one piece to the other. To clarify that, let's call this here piece 1, this here piece 2, and then this here piece 3. And there is effectively some glue that holds them together, right? So this glue holds them together, but I'm an engineer and I want to know, hey, how strong does this glue have to be? And to figure that out, I just take it apart and then pretend, I took the force away from the glue. How much force do I need to bring it back into place? And to conceptualize that, let's just pretend for 1 second that we have a force here on the system, on the table. So let's say I have a force that acts exactly in the middle with, I don't know, let's say 10 Newton. It doesn't matter really right now. Maybe it's 1 Raphael, maybe it's 1 student. It doesn't really matter. But now you know from symmetry and things that we talked about before that, of course, each support reaction here has a resistance. And in this case, with 10 newtons on top of it, of course, we have 5 Newton pushing up here because it's symmetric. And then I also have 5 Newton on the other side. Okay, and now you can already guess where we're going. I took it already apart for you here in the pictures on the bottom. So let's bring down our reference fiber first, and let's see how the system looks after we cut it apart and what forces do we actually have to deal with. So in the middle piece, I have, of course, my 10 newtons that's pointing directly down in the center, 10 Newton here. And I have my support reactions, which are in this case 5 newtons on each side. But we don't care about the specific numbers here right now. Right now I just want to symbolically introduce to you how these forces work and what we just done. And what we have done is we actually created imbalanced systems. So we have 3 systems here, and in fact, to make that 100% clear, let me introduce the numbers. This was member 2 and this is part 3. And each of these elements are now separated. We cut through the glue and these systems are not in balance. So this one here is with an imbalance up with 5 newtons. This one is with an imbalance down 10 newtons and we have an imbalance here. So the glue at this connection here really made sure that we somehow can transfer the 10 newton from the center to the support. And so far this has just been accepted as magically happening for us, but now we want to learn how that works. So the question we really need to ask ourselves is, what do we need to do at this surface here and this surface to bring the system back into equilibrium? And we can do this piecewise. We can first bring this back into equilibrium, then bring this one back into equilibrium, and then this one, or in any random order really. So you may already understand why I'm using a 3-dimensional description on top of this 2D dashed fiber or the 2D system that I used here and here, because we want to represent this glue here. The glue is really what keeps this surface together that would not be available to us if I would just look at an X-Y coordinate system. But we need to understand what's acting on this surface here, which is the glue line. So let me actually add these 2 diagonals here so that we understand better that the force is actually acting on that surface that we will now introduce to bring our systems back into equilibrium. And of course I can do this for all of the individual surfaces that are seen here, but please understand that they're also available on the surfaces that are away from our view right now. But to show these a little bit better, let me actually draw some faint dashed lines here in the background, because those are the surfaces opposite to the ones that we can see here. And those, of course, have to also carry some forces to transmit the loads between one side of the glue to the other side of the glue. So that's what you see here now with the dashed line. Okay, so now we can ask ourselves, how do I bring this piece, element number 1, back into equilibrium so that it doesn't fall down here on the glued line, because it didn't fall down up here. I just virtually cut the system and pretend that I'm analyzing the glue now. So what do I have to do? Of course, you already see that it's in imbalance in the vertical direction. Therefore, I need to somehow bring a force into the system that pushes against the 5. I don't really care about the values here, but I care that I need to balance the vertical direction. So I actually need a force that is pointing down here. Now, what is this force doing? It's pointing down, but it's also parallel to this surface, if you will. It's not perpendicular, it's parallel to the surface. And so you may already know what these forces are called, but think about what a force is that is parallel to a surface. Exactly, it's a shear force, right? So engineers call that a shear force, but the layman calls it a shear force too, actually, because if you think about the scissors in your home, what do they really do? They have two surfaces, just like this glue and this surface here, that shear parallel to each other. That's why we also call scissors shears, right? But now we have this imbalance, or we can potentially use this force to bring the system in the vertical direction in balance. But the trained engineering eye already sees that these forces, even if they have the same value, 5 Newton and 5 Newton, they would cause this system or this rigid body or the part of the body to rotate. In this case, it would rotate clockwise. So we need to do something against that. We need to bring in a force or some system that prevents rotation. And of course, you already know how that works. You know that you can use a moment, because a moment is the tendency to rotate. And so this rotation that the 5 and the 5 here would cause clockwise can be resisted by this tendency to rotate in the opposite direction. So this here would be the moment. And now you may think, this is in equilibrium, and seemingly that is correct. But we need to understand another thing, that we could in a 2D system have yet another type of force, which in this case actually happens to be on the right side. It's here where the pin is, because the pin also resists forces in the horizontal direction. So we need for the glue to be able to also transfer horizontal forces from element 1 to element 2, right? So there needs to be a force here that actually acts in that direction. And to no surprise, we can draw that with a force that is actually acting in this direction, which now is perfectly perpendicular to the shear force and to the surface that is acting there. And because this is actually perpendicular to the surface with the green diagonals, we call that, exactly right, we call that a normal force, right? So this is a normal force because it acts normal on the surface. And once again, you see why I'm using a three-dimensional picture to describe something that we will analyze in 2D, because we would not understand why this is called a normal force or a shear force if we did not have this surface available to us. This surface really gives rise to the name normal force and shear force. But now, in a two-dimensional sense, if you look at this picture without these diagonal lines, these three entities, the shear force, the normal force, and the bending moment, are capable to keep this glue and the system in equilibrium. Of course, in this case, the normal force here is 0, right? Because there's no external force acting here. But we still need the glue to be able to transform that. All right, now we have one system in equilibrium. The next easier one is probably the part 3 here. So the system 3, let's put that into equilibrium. And yes, you guessed it, we of course need a shear force, a normal force, and a bending moment as well. So let's introduce those forces too. We need a vertical resistance in the glue. We need a horizontal resistance in the glue. Again, these two are perpendicular to each other. And we need a moment that is strange to see in this case, but we need something that prevents bending as well. And right now, I'm not really concerned about the direction. Of course, we kind of intuitively feel that the force here should be pointing downwards. The normal force, as you will see in a second, always points away from the surface. And then the moment also has a special definition usually, but we will see that later. It really rotates clockwise in this element 3, and you will understand why this is a different rotation than this one here. Of course, I could have also put the arrowhead here on the bottom side, but there's a specific reason that we will talk about in just a little bit why this is pointing or rotating counterclockwise, where this one is turning clockwise. And similarly here, this is pointing to the left and this is pointing to the right. And the reason for that really is because we're trying to pull away from the surface and pull away from the surface. All right, so now with these three forces, we also have element 3 in equilibrium. So now we have to put element 2 in equilibrium, because while this is not falling down or rotating, and this one is not falling down or rotating, this one can technically still fall down with 10 newtons. So we have to balance this. And one important thing to note is if I put the first surface into equilibrium, let's say for the vertical forces, then yeah, you may think that now this could be in equilibrium because I have something pointing up and something pointing down. But notice once again that these two forces actually rotate the system. And even if I bring in a moment here on this side now, it could still rotate the system. So what do I have to do really? I, of course, have to bring in a force on the other side that actually can prevent that rotation from happening. So I would end up with something here. And to keep that in equilibrium, we have to point upwards as well. Now the next easier one to deal with is the horizontal force or the normal force, which has to once again pull away from the surface. So I'm drawing them in these directions. And keep in mind they are perpendicular to each other. And notice a very important thing here. This force at the glue can balance this force at the other end of the glue. This normal force applies a force to this glue that is opposite to the force here that is applied to this glue, if you will. And so these cuts here, the space in between is actually in equilibrium if you want to think about it this way, because this force is pushing on the cut and this force is pushing in the opposite direction on the cut. And so what I'm trying to tell you is that it doesn't matter if you only look at this system here, only number 1, or if you look at 2 and 3 together, these forces, the normal force here, comes out to be the same as it would come out here on this side. So you can think, of course, of this system being 1. So forget about the cut that we made here. This system together would be the same as this one at this cut here. So therefore you understand that this is not really in equilibrium yet, because on the left side to it you have a bending moment that is also presented to the cut, and on the other side as well from element number 3. So we need to balance this rotation and we need to balance this rotation. In other words, I need something that resists bending here in the glue, and I need something that resists bending there. Now the question is, in which direction should they rotate? And the answer is already available here. So for element 1, we have an arrow that actually rotates counterclockwise. So to balance this counterclockwise rotation, this here has to rotate in which direction? Exactly clockwise. And if you look at the other side, you can argue two ways now. We don't know if this is rotating clockwise or counterclockwise, but you can say, hey, there's a rotation in element 3 that actually rotates clockwise, therefore this needs to be counterclockwise. Likewise, you could use the argument that element 2 has to be in balance in total, and if this is rotating clockwise, then this one here has to be counterclockwise. So that brings up or concludes the important point that the left side has to always balance the right side, for example. Or another way to look at this, if I look at element 3, I can say that element 3 here is in balance now, just with the same values as element 1 plus 2 would be at this glue line here as well. So everything to the right is the same as everything together on the left. And that is an important concept to understand. So now you know that we have always on these surfaces 3 forces, the shear force, the normal force, and the moment, and that they always have to be in balance with the other side, with the opposite side. Otherwise, the system would not be in equilibrium, and if the system would not be in equilibrium, then the glue would not hold it statically together, right? So this glue line here makes sure that element 1 and element 2 are together in equilibrium. And that equilibrium is just shown symbolically here. So the direction of these arrows is not how you will see them later on. So please do not get confused when you study this in the context of this picture here. This picture just tried to explain this conceptually, that you have to push in one direction and keep that in balance and rotate it into balance and so on and so forth. But we will later have a precise definition of when an arrow has to point up and when it has to point down. This may not be consistent with what you see here, but this gets the point across. And with that said, I believe we now have enough insight to move on and talk about the real definition, at least from a mathematical standpoint, of the internal forces. So what type of forces did we talk about here? We talked about 3 different systems. First, we talked about forces that were normal to the surface that we cut. So forces normal, or you could also say perpendicular. To the cut surface. Those are forces that were also, in other words, parallel to the x-axis, right? So forces parallel to x-axis. And we called these type of forces normal forces, right? So let's keep in mind that we call these normal forces. And I believe the name is clear now why we call them that way. But just to be sure that we understand in which direction they act, let's draw our rigid body here with those forces. And we used purple colors for those. So we actually had forces that were acting in this direction. So we call these normal forces. And those normal forces can either be in tension or in compression. So for example, if they pull away from the beam, then they obviously put the beam in tension. So this system here would be in tension. And so we call a positive normal force a system in tension, whereas a negative system would actually be in compression. And that is very important to understand, because sometimes engineers blindly communicate if a system is in tension or in compression. So if you see a normal force that is negative, that would mean that this arrow here would be flipped around and would actually push on the system on both sides, and therefore the system would be in compression, whereas if you pull on it, it's in tension. And so you may understand that engineers use this very effectively, because every column by definition has to be in compression. Otherwise it would not be a column, right? A column is something that carries vertical loads. And so engineers know by default that the normal force in a column is negative. And they use that effectively to communicate if it's in tension or in compression by means of the normal force. Now we also have forces that are perpendicular to the x-axis, or forces that are parallel to the cut surface. And since they are parallel, they really produce shear, right? And that's why we call them shear forces. But you can also think of these as forces that are perpendicular to the x-axis. And once again, we call these shear forces. So shear forces. And the way we indicate those in our two-dimensional description is really with vertical perpendicular forces. And please note that now I'm starting to use the right directions for them, although we haven't really discussed that, but I will define that for you later. But they act in these directions, and these are called shear forces. Last but not least, we also have bending forces or bending moments, so moments around the z-axis really. So we have bending moments around the z-axis. And this is something that in a 2D description, of course, makes sense in the context of the right-hand rule. You understand that everything that rotates within an XY plane rotates about the z-axis. And so we call these bending moments. So let's write that down. These are bending moments. And the way we identify those is really with the semicircles that rotate on one side in one direction and on the other side in the other direction. And mathematically correct would be to have them rotate this way around. Now, why does it make sense? So this is very important in the context of the reference fiber. The way I look at this is that these create positive bending. And what is positive bending? Positive bending is really elongation of the reference fiber. What do I mean by that? So you can, of course, bend a system so that it smiles. So for example, you can have a system that puts the reference fiber in tension, and that is really only possible if you use your internal forces to bend this way around. And I sometimes give this guy some face and some hair. This is a happy guy, this is my friend, and this would be a positive moment, right? So this would be positive moment. He puts the reference fiber into tension, and then I have the guy that is upset, and that guy would really look like this. And I have the reference fiber now in compression, and that is because the system would rotate in this direction. And now he is very sad, maybe he's even shedding tears. You can see why I became an artist and not an engineer, because I'm so good at it. So he is very upset, and this would be a negative moment. So negative moment. And of course, this guy here is a happy guy, right? He is happy because the reference fiber is in tension. Think about this. Take two stacks of paper, lay them on top of each other and bend them this way. The bottom one will be in tension, the top one will be in compression. And so that is defined as a happy moment. Whereas, of course, this guy here is very sad because the reference fiber is actually in compression, and that makes a negative moment. But this takes us into the mathematical definition that I will define very clearly for you on the next page. For now, let's just understand that no matter if you have positive or negative values, everything has to be in equilibrium. So for example, here on the left side, you have a force that points to the left, therefore here it points to the right. So this element can be in equilibrium. Same thing here, you have a shear force that is going up and here it's going down, therefore the system can be in equilibrium. Of course this would rotate, but we have the moment as well that can prevent that, and if the moment is turning clockwise here, then it has to turn counterclockwise here. And by definition, you just have a positive moment when you have tension in the reference fiber, and a negative moment when you have compression in the reference fiber. Now, of course, engineers need units for these forces, which are not surprising to be, for example, in force units here. For the normal force, of course, the shear force is also in force units, and the moment is in force times distance. And that is how we describe them. Sometimes we need a short form for them, or we have diagrams in which we try to indicate that it's a normal force, a shear force, or a bending moment. And that is usually done with this little circle symbol. So normal forces we indicate with an N. Moments we indicate with the M, and you would think that shear forces we do with an S now, but no, because it comes out of a different language, we are using a V. So we describe the shear forces with a V here. And those are the things you need to memorize, that you have normal force, shear forces, and moments. They are always in equilibrium, as you can see here. They always have to balance the left side with the right side, but we will talk more about this on the next page. So now we understand where the force definitions come from that cut surface, and how we need to look at them and how engineers try to abbreviate them. So now that we are aware of these definitions and the general introduction of the internal forces, we will look into how to mathematically set up these problems in which we are asked to find internal forces. And again, think of those as finding the force of the glue that keeps the rigid body together. But I will do that with you on the next page. So let's move on to there. All right, now let's look into the internal forces at a specific point in a rigid body, for example, as you can see here. So think of point C as the point where we're trying to find our internal forces. Let's first take a close look at this rigid body, and let's understand that we have external forces, F1 and F2. Those are given to us usually. And then the first thing we do, and the things that you've done in your last 3 homework assignments, were to find the external forces that are not given. So the support reaction at A and the support reaction at B. And you will have to continue to do that for each upcoming problem now. This is really the first thing you have to do, and that's why it's so important that you're so proficient at finding support reaction, because the support reaction define the internal forces. And if you do not get the support reactions correctly, then you cannot find the internal forces correctly, in this case at location C. So what do you do after you have the support reactions? You would then go ahead and virtually cut the system. That's how engineers say that, right? So we would cut the system at location C, and then we can separate the system. So we would either look at the entire right side of the system or the entire left side of the system. And I usually call these things cut clouds. People give them different names, but pretty much what we do is we separate the system at the location where we're interested in the internal forces. And then when we cut this, so let's think, for example, of this cut. If I were to draw that, let's do that here on the bottom. If I draw that cut, then my system would really look like this. I have, of course, my reference fiber that I cannot forget. I have my support reactions and my external forces. So here I have F1, here I have usually RAY, and then here I have also in this case a force that in this case points to the left, but in reality it points to the right because F2 is pointing to the left, and so we're balancing that with RAY. And from now on you understand that I cut the system here, which is really at location C. So this is location C. And this system, of course, cannot be in balance because, yeah, maybe F1 is equal to RA1 and then it would all be in vertical equilibrium. But again, you would have rotation, so it cannot be. And by the way, F1 here would not be equal to RAY unless it would be a very special case. And therefore, there's not even a vertical equilibrium. So what you have to do is you have to bring in your internal forces, which now, by the way, are external forces, right? So by me cutting the system here, and sometimes I give this a name, like I call this here cut 1, and I call this here cut 2. And of course, here I have given cut 1. And because I have extracted cut 1, the glue here is now out of balance, and I have to put that back into balance. And the trick that engineers use now is, hey, what happens if I take that away? So the forces that I take away are the ones that you have seen before. I have a vertical force, I have a horizontal force, and I also have a rotation. And again, this here points actually in this direction. In this case, this has to go in this direction, and this has to go in the counterclockwise direction. Why? Because this is actually a right cut. And if there's a right cut, there must also be a wrong cut, right? No, I'm just kidding. That's actually a right cut versus a left cut. So here we would have a left cut. And so this definition here, as you will see on the bottom of this page, the definition in which direction these forces point is actually defined by the left cut or the right cut, but I will come back to that. But for now, understand that I have M of C here, I have V of C here, and I have N of C. And now I can calculate these. If all the other forces and dimensions are known, everything in blue here would be known and the length would be known, then I can calculate MC, VC, and NC. And I say it again, the trick that engineers use is we pretend that this is not there initially, and what is the imbalance that I have to balance or bring back into equilibrium by using these purple forces here. And hopefully you are looking at this right now and you say, this is actually an easy problem for me now because I can already calculate these forces. This looks exactly like what I've done when I solved cantilever problems. So when you were solving cantilever problems, all the forces were given to you except the force at the cantilever. And what forces did the cantilever balance? It balanced a vertical force, it balanced a horizontal force, and it balanced a moment. And this is exactly the same. So mathematically, you already have all the tools in place. You just need to understand how to apply it. So you know mathematically what to do. We just need to find out how we do it. But I think I already gave you a first insight. You cut at the location where you try to find your internal forces. You redraw your free body diagram. You are missing forces that can keep it into balance. Then you add the forces. You draw them into your free body diagram and then you calculate them, and nothing is easier than calculate them by using the three equations of equilibrium. The sum of the forces in the y direction being equal to 0, the sum of the forces in the x direction being equal to 0, and the sum of the moments about the z-axis being equal to 0. Now, you already understand that I can of course draw the other side of this cut as well. So for example, if I wanted to look at cut 2, I would just have the very same system that looks in this case then like that, with a force here and a sloped force here, which we called F2. This here would be RBY. And of course this system as it looks right now is not in balance, but this would be cut 2. And this actually happens to be a left cut, which by the way is the right side of the system, right? So this is the right side of system. So the beam is really the right side here. So this is the right part, but because the cut is on the left side here, it's called a left cut. And now this of course is not in equilibrium. You can see that right now. So I have to bring in my external forces, which ultimately are the internal forces. But because I made the green cut there, I now actually have external forces, a vertical one, a horizontal one, and a moment, if you will. And of course, they now have to balance whatever I have defined here. So therefore, they point upwards, they point to the left, and they rotate clockwise in this case. And of course, they are also N of C, V of C, and M of C. And now the left side is in balance with the right side. This is always the case. And this is just shown conceptually here, but with numbers, this will come out to be the same, as you will see when we solve our example. Now, the picture here on the bottom is the same thing, just a little bit nicer. And you understand that, of course, it has the reference fiber missing. But other than that, it shows you the same concept. So let's use this picture here to clarify that we're talking about the right side with left cut. And here on the other side, we're talking about the left side with a right cut. So I say it one last time, we cut the system right here and right here. And of course, there's a left side and a right side to it. But with that said, I believe we now have everything in place that we need to know to conceptually solve these problems, except the one thing is the mathematical definition of when a value is positive and when a value is negative. But for that, I'm going to move on to the bottom of this page to talk about the mathematical definition of internal forces. So let's move on and talk about the mathematical definition of the internal forces. And what we develop here is something that is probably not even worthwhile memorizing right away, or don't fool yourself in memorizing it initially. If you taught the class as many times as I did, then you probably will be able to remember what we're going to put here now. But even if we take it as a closed book, closed note exam, I always recommend my students to bring this on a study card so that they can use the study card as a reference to memorize what the positive definition of the internal forces are. So let's go ahead and draw this, and please put it into a study card that you always have handy. So first I'm going to cut here and I'm going to cut here, and I'm going to call this here the right cut, and I'm going to call this, of course, the left cut. And now I bring in all the positive values. Of course, you may think that you have seen these before, and that's partially true, but sometimes it's not true. Some of the forces that I used were not properly defined positive as they are here now. But I will now use the absolute correct definition in reference to the reference fiber. So the reference fiber defines what is acting positive in which direction. And the first thing I'm going to start with is my vertical forces. So I have a vertical force on this side and I have a vertical force on this side. I also have horizontal forces, and that applies at both sides. And I have a moment on both sides. This looks like that. Now, on the right side, I have a normal force that points to that side. On the left side, it's pointing in this direction. Then I have a shear force that goes in this direction and a moment that goes in that direction. And don't be confused, it's mostly similar to what I've done before, but now I want to be very clear why it is as it is mathematically defined. So here we have a positive V, here we have a positive N, and we have a positive M. And the same is true here, positive M, positive V, and positive N. And I want you to think about this. The reference fiber here really tells us in which direction the moment is acting and where the left and the right is and so on. And I want you to think about how long this reference fiber is. This element here could really have any length, right? So I could now say that this even has a length of dx. So it's super tiny. It could also be 5 meters. It doesn't really matter. But often later on, we will actually use this in terms of x. And remember something that you have seen in your homework. You may have not known why it was there, but sometimes you've seen that there was an x direction given with that pointing arrow. Now, why is that important? Because later on we will express the moment as a function of x, the shear force as a function of x, and the normal as a function of x. So sometimes you would say, like before we said in terms of c, right? Or sometimes, let me erase this here, sometimes you may say, hey, this is equal to x being 5 meters, for example. But really, the way we want to say this is we're going to say that it's just the normal force of x, the shear force of x, and the moment of x. And the same is true here on the other side, depending on which side you cut the system. So this is the shear force of x and the normal force of x. And last but not least, let's understand that this here is the positive side, right? So this is positive, this is negative. Now, why is this important? It is important because later on you may not have the reference fiber on the bottom, or you may not have a horizontal member. So then you need to actually bring this notation here and line it up with your actual problem at hand. So what you should probably do is go ahead and cut a little card out of paper. I of course cannot do that, so I'm just going to highlight it here for you. So I'll take this and would technically cut it out. And after I cut it out of paper, what I would do is I would fold it in half right along this line here so that I can use either the left or the right cut and line it up with my problem that I'm currently dealing with. But you will see through application how that becomes beneficial. However, I say it again, in the classroom, I would always encourage my students to bring this card and always have it on them when they solve problems for engineering mechanics. And again, there's no need to convince yourself that you know these definitely from the top of your head. I've seen many students trying to memorize this, and in different scenarios, it goes wrong. So this is a good advice from my point of view to you, that you should always bring this and have this on hand as you solve internal force problems for engineering mechanics. But this now provides all the knowledge we need to actually go ahead and start applying it. Of course, through application, the concept will become more clear. I wouldn't expect anybody to be able to do this right now, how to calculate the normal forces, shear forces, and bending moments. But that's why I will show you on the next pages how to find them for actual number problems. So let's go ahead and start solving our first internal force problem. So welcome to your very first internal force problem that comes in a very specific form, as you can see here on the top of the page. In fact, it comes in a form that you won't see later ever again. So let me explain what I'm talking about. So the problem asks us to determine the internal forces, normal force, shear force, and bending moment at specific locations. And this is the only time you will see this at x equals to 3.9999999 meters, at 4.000001 meters, and then you can read the other numbers here, right? But what I'm trying to explain to you here, or what I'm trying to make clear to you here, because I sometimes see this go wrong in the classroom, is I want you to understand that you can have a 4-meter distance x here, notice the x here on the bottom, that is actually acting to the left of this force, and that would be 3.9999999. Or I can have 4 meters just to the right of the force, and that would be 4.000001. And again, no engineer right in their mind would say it like this. An engineer would probably more say it like this. But later on, we will just say at 4 meters. In fact, later on, you will just do it at every instant along the beam. So you will do it in terms of x. But for now, let's just go ahead and calculate the forces at x equals to 4 to the left of the concentrated force, at 4 to the right of the concentrated force, at 5 to the left of the concentrated force, and at 5 to the right of the concentrated force. So let's go ahead and do that. As we know from our explanation before, we need to find the support reactions first, but keep in mind that we actually already solved the problem in lecture 10. And so I already remember that my support reactions were as follows. I had a support reaction that was going up here. I had a support reaction that was going up here. And I had a support reaction that was acting in the right direction on the left side. And the numerical values here were really 43.3. And the vertical one was 11.43. And the second vertical one was 23.57. Of course, all in Newton in this case. Okay. So now I have my external forces. Now remember what I need to do. I need to go ahead and draw my free body diagram for specific cuts. I'm going to make a cut here. That's going to be the first thing I'm going to do. I make a cut here. That's the second thing I'm going to do. And then third here and fourth here. But I will do that on the next page where I prepared free body diagrams for these specific cuts. So I will see you there. All right, so now I have prepared something for you. Actually, the first 2 cuts are prepared. So let's take a look at the very first cut here on the top. And as you can see, that cut actually has a length of 3.999999 meters. And remember that the first thing I need to do is bring in my external forces. So what external forces did I have? I had a support reaction here that was pointing upwards. I have a support reaction that was acting horizontally, and they had values of 11.43 and 43.3 Newton. Now, this cut is currently not in equilibrium, so I'm going to bring in my internal forces, which are technically now external forces because I made a cut here. And the forces that I bring in is my moment. I will bring in a shear force, and I will bring in a normal force. Now, in which direction should I point them? I should point them according to my study card, and you of course have this in front of you. You have to trust me that I have this in front of me right now here as well. So my moment would go in this direction, my shear force would go in that direction, and my normal force goes in that direction. Why? Because I folded my card in half and then lined up the dashed fiber here, or the reference fiber here, and then I knew in which direction I have to do that because I have a right cut here. Okay, so I should also name these. So for example, I should call this here moment at 3.9999. I'm not going to write this all out. Here I have V of 3.9999 and so on. And I have the normal force of 3.9999 and so on and so forth. Now, how do I solve this? To no surprise, very similar to solving cantilever problems, because in a cantilever problem you have the three support reactions that are unknown. So these are my three unknowns that I will solve for using the three equations now. But the only difference to a support reaction problem is that now I'm bound by the positive definition. So this is already positive defined. So if it comes out negative now, I will not flip it around. I will just leave it as such and call it a negative normal force or negative shear force, negative moment. So from now on, I call it positive or negative. I do not flip it around. So let's go ahead and calculate the sum of the forces in the x direction. 0 is equal to, I start with my unknown, plus, and I say positive n 3.99, and I use a double positive on purpose here, and plus 43.3 Newton. And therefore my answer here for n at 3.999 is really equal to, now I have to be careful, negative, right? Negative 43.3 Newton. And yeah, you would say that, hey, negative means that my arrow now points to the left, and that is correct, but engineers have a specific meaning of the negative, and it means that the negative now puts this into compression. So an engineer would say that this now is a compression force, because the member here is actually now in compression. But this is my result for the normal force at that location, so I can double underline it. And I can move on to my shear force. Now, how do I move with my shear force? I always start with my unknown as well. So let's go ahead and understand that it's actually pointing downwards, but it's positive, right? So I use, again, two signs here. I have a positive V 3.999, but this positive defined one is actually pointing downwards, therefore it's negative. And now this is hopefully balancing the plus 11.43 Newton. And therefore I know that my shear force at 3.999 is really equal to positive 11.43 Newton. And that now will not be interpreted other than that the shear force is positive. So I don't say it's up or down. It's relative to its positive definition here. And notice that I brought in my positive definition and I found it out to be positive. So that is my shear force. Last but not least, I use my moment counterclockwise positive. And I start again with my moment here with my unknown. So plus positive defined m 3.999, and this is again, this plus here stands for hey, I'm following this arrow in my drawing, but it now turns counterclockwise, which makes it positive. So I use a double plus. And some people wouldn't do that, but I think that gets the point better across, at least as you solve more of these problems. Even though initially it confuses more, but it is more precise if you think about it. All right, so now what do I have to do? I have to rotate about this point, right? Remember when you found the moment for your support reaction of a cantilever, you took the moment about this point. And so I do the same thing here now with my 11.43 times its lever arm. So really what I would be writing here would be 11.43 Newton multiplied by 3.99999 meters. Yeah, and now in which direction does that rotate? That clearly rotates about this point in the clockwise direction. So let's make that a negative. And just to be clear, this is all negative. So therefore, I know now that my moment at 3.999 is equal to positive 45.72. And that is, of course, in Newton meters. And the positive here now doesn't tell you clockwise or counterclockwise. It technically does tell you that, but we are dealing with internal forces, so we're not flipping anything around anymore. So I'll say that again. We just state either if it's a negative or a positive. And I want you to always include the positive. Do not forget the positive. Your answer for internal forces should always have a mathematical sign. Even if it's positive, you need to indicate that it's positive. And this will become more important later down the road. But this now completes our first cut for the free body that we have drawn up here. Just before I move on to the next cut, which would be to the right of the force that we cut here before. But before I move on to that, please understand that this is identical to actually solving the opposite system, which would be on the right side. So I think it looked something like this. I had a support reaction on the right side, which was called RBY, and I believe that was equal to 23.57. I also had two other forces acting. One was directly at the cut here, which was 10. And then I had a sloped force here with 50 under an angle, so 50 and 10. And if you were to make this cut here now, you would find that you have the same answers for your shear force and your normal force and your bending moment. Of course, they would point in other directions now. So for example, the shear force would go in this direction, moment would go in this direction, and the normal force would go in that direction. But this would be equivalent. And hopefully this doesn't confuse you. You may think like, how can this be equivalent? Because there's more forces acting on here. But keep in mind that here you have different support reactions than you have here. And of course, if you glue the system back together, these forces have to disappear, right? And that's something you can actually verify. And this is why this is such a nice class. When you take an exam, for example, you can be 100% certain that these answers are correct because you can verify them yourself before you turn in your answer. And so this is really a very beautiful way to look at these problems. And I believe we can use this concept now for all the following cuts. So let's move on and talk about the next one. The next one is the one down here where we're actually looking at the same system, but now we're adding a force into it because we are now to the right of this force. And so let me redraw my free body diagram here, or complete my free body diagram. So I had this force and I had a normal force, sorry, not a horizontal support reaction. This was 43.3, 11.3. And now I bring in my study card again, which of course looks exactly the same as it did before. So I had a vertical force and I have a horizontal force and a moment. And the way they are pointing would be in this direction. And now we would talk about M at 4.0001, V at 4.0001, or however many zeros you want to add there, and N at 4.0001. And what I'm really trying to tell you here, or try to make clear to you, is that you can cut just to the left of this force. That's what we did in the previous cut, or just to the right of this force. And so here we're cutting to the right. So now my equilibrium equations look slightly different, but maybe for clarity I also use proper colors this time. So I start with my normal force and I say plus n at 4.0001, and this now is actually in the positive direction, so plus. And now I need to include the 43, so plus 43.3 Newton, if you will, and that is also acting in the positive direction. So therefore we will find that our normal force actually did not change. It's in fact the same equation because there's no normal force added to the system. So we will find that my n of 4.000001 is actually equal to negative 43.3 Newton. And that is once again a result. And yes, it's the same result, but you were asked to solve it at that location, so therefore we need to underline that. All right, now up to the shear force. We start with my unknown. So this is positive defined V of 4.000001. And of course, I understand that it's actually pointing downwards, and so therefore it's negative, right? It's not positive, but it's positive defined, and that's what I tried to indicate with the purple color. Now my red color is acting positive 11.3 Newton. And just to be uniform here, I also make that positive positive. And I now need to actually include this 10 Newton here. So therefore I also have a positive 10 Newton because a force is always positive in a diagram, but it's acting in the negative direction, so therefore it's going downwards. And now I can close out my equation and I can identify that my shear force at 4.000001 is equal to positive 1.43 Newton. Now that will be a result once again, so we obviously double underline that, and notice that I used a positive in my answer here. Last but not least, let's go ahead and calculate the moment. So that would be positive defined m at 4.000001, which I put in parentheses, and now it's also turning counterclockwise. That makes it positive according to my definition here on the left side. So I now include my 11.3, so plus 11.3 Newton, which of course is always positive defined, multiplied by 4.000001 meters. And that has a rotational sense as well, which about this point here rotates clockwise, therefore it is negative. And then I can calculate my moment at m equals to 4.000001 meters. And surprise, surprise, it is actually the same as before, which was plus 45.72. So plus 45.72 Newton meter. It is a result, so I double underline it. And I want to talk about it real quick. You may wonder, why did I not include the 10 here? And maybe you already know the answer. It's because this 0.00001 meter is effectively 0. And so I kind of left this out. I mean, you could have added 10 times 0.000001, but you would see that it has no impact on here. And that's what I was trying to show you actually with these strange numbers that I used instead of saying 4 meter to the right. So now if you compare these two cuts on the side, you can see that there are some similarities, but also some differences. And because I cannot flip back and forth between pages here, I'm going to do it here. Usually I ask my students to do this at the end of the problem. But since we're here, let's look at it. For example, the normal force did not change, right? Why? Because the normal force did not include any additional forces between this cut and this cut. In other words, this cut and this cut in the formula was identical. Now for the shear force, that's a little bit different, because here we cut just before the force that would be coming here, that is actually included in this system, the 10 Newton here. We did not have that included here. But here we had it included. And therefore we actually have a difference of 10, right? So we have a difference between 11.43 and 1.43 that is equal to 10. And that difference is actually given by this force here. So the way this equation is different from this equation is indicated by that 10 here. Now, for the moment, you did not really have a difference. Simply, the lever arm became a tiny bit longer from 3.99999 to 4.000001. Is really no difference, and therefore the result here is actually identical. And you may think, this is not true because technically there's some difference, but from an engineering standpoint, no, there's no difference in that context. And that concludes the first cut at 4 meters to the left and to the right. And now we're going to move on to the cut at 5 meters, and we do the same thing. We cut at the left side and we cut on the right side, but I will do that on the next page. All right, similar to what we have seen on the previous page, we now have 2 cuts, one at the top and one at the bottom, that are almost identical, except here we're cutting to the left side of the force, the 50 Newton, whereas here on the bottom we cut to the right side of it. And so we get slightly different equations here than we get down here. So let's dig in and let's start with our first cut here. And as always, we have to bring in our external forces first. So let me start here with RAY, which I believe was 11.3, and my horizontal support reaction was equal to 43.3, pointing to the right. Now I want to bring in my cut. I'm cutting right here, and I therefore have to now bring in my external forces, which are technically internal forces, but I bring in my shear force, I bring in my normal force, and I bring in my moment. And of course, I need to assign proper direction according to my study card. The moment turns according to that counterclockwise. My shear force is going down and my normal force is pointing to the right. I need to assign proper names. So for example, M at technically 5. So what I'm going to do now is I'm going to call this 5 to the left, and I call this 5 to the left for the shear force as well, and for the normal force I also call it 5 to the left, which really is equal to 4.99999, but in reality engineers would consider that being 5, so I call that 5 to the left. All right, now we can write out our equations as always. I can go ahead and start with my horizontal force, and I start with my unknown. So plus N5 to the left, that is always a positive identifier, but it's pointing to the right. And because it's pointing to the right, therefore it is considered positive. I now use my 43.3, so plus 43.3 Newton, which is also always positive because it's in a sketch, but maybe to be unmistakably clear here, it's also pointing to the right. And therefore I can now say that my normal force in the 5 to the left location is equal to minus 43.3 Newton, which of course means that it's in compression. And now I can double underline that because it is my result, and I can move on to the next shear force. So the shear force here, I start with that unknown. Again, it's always positive, V of 5 to the left. And yeah, I understand that it's not really positive according to what you think, because it's pointing down, but I do that with my black identifiers here. In the parentheses, I always remind myself that an arrow is always positive. So now I have to identify that it's actually negative going downwards. And what's acting with it or in the same direction is the 11.3 Newton. And to be consistent, I also make that positive and put it in parentheses. But that is acting upwards, so I'm going up there. Last but not least, I have to consider the 10 Newton up here. So I also have a plus 10 Newton, which, yes, it's pointing downwards, but I indicate that with my negative here to be unmistakably clear. And now I can solve this equation and find that my shear force at 5 to the left of the force is really equal to plus 1.43 Newton. Think about that. Maybe you have seen that somewhere before. I will talk more about this when I solved all of it, but maybe you can already identify why that number came out to be that way. Let's go ahead and solve the moment. So the moment, of course, again, is positive defined, 5 to the left, but it's rotating counterclockwise, therefore it's positive. And now remember that we're taking the sum of the moments about this point. In fact, I indicated this for you here, x equals to 5. So I really have to take the 11 and the 10 and rotate it about this point. Now the 10 actually does have a lever arm, but we'll come to that in a second. Let's first start with the 11.3 Newton multiplied by, what's the lever arm? 5 meters, right? Or 4.999. So 4.99999, which is really 5 meters. Put this in parentheses or brackets and give it a rotational sense, which in this case is really clockwise. Therefore, we'll make that negative. Now we also have to consider the 10 Newton in this case. So 10 Newton multiplied by 0.9999999 meters. And that also needs a rotational sense. In this case, it rotates about this point, which then means counterclockwise rotation. Therefore, it's positive. And now I can solve for my moment at 5 to the left, which comes out to be equal to 47.15. So plus 47.15 Newton meter. And by the way, remember that the positive and the negative for a moment also have a specific meaning, just like the positive or the negative have a meaning for the normal force, negative meaning compression, positive meaning tension. The positive moment means the beam is smiling, right? It has tension in the reference fiber, whereas a negative moment would mean compression in the reference fiber. And since here you have a simply supported beam where all the forces come from the top, the beam can only smile. It has to bend downwards. And therefore, it makes perfect sense that we only get positive moments so far. But we'll talk about this again when we solved the problem completely. Now we have all the numerical answers here. Let's move on to our last cut. And that is for 5 meters to the right of the force. So once again, we cut the system right here. We bring in our forces. So first we have the external forces, which are the 11.3 and the 43.3. And because we cut right here, we now have to go ahead and bring in our external forces, which are technically internal forces, but through the cut we turned them into external forces. So that's our little trick here. So I bring in my shear force, my moment, and my normal force, and I give them proper names. So N at 5 to the right side, V at 5 to the right side, and M at 5 to the right side. And please understand that now we have a force here that acts under an angle. Let me remind you that that angle actually was 30 degrees, right? So we had an angle alpha here that was 30 degrees. So 30 degrees, we will need that in our equation later on. In fact, we need it in our first equation. So let's go ahead and write out the equation for the normal force. I start with my unknown as always, so plus n at 5 to the right is pointing to the right, therefore I make it positive. I now bring in my 43, so plus 43.3 Newton, which needs a direction as well, happens to be positive. And now I need to add actually this 50 Newton times the cosine of 30, right? So I have 50 Newton, multiply that by cosine of 30 to get the horizontal component, or the component that's parallel to the x-axis. And then I need to identify that this is positive in this direction, but it is negative because it points to the left. And now the system is actually in balance before this force is actually applied. So the system from here to here is in balance. In fact, if you think back how you calculated the support reaction, you know that this 43.3 is just equal to 50 times cosine 30. And so now your normal force actually goes to 0. So we can say that therefore our normal force at 5 to the right is really equal to plus minus 0. And that is a result, believe it or not. So you cannot get away with just leaving it out. You have to calculate it, and you have to mathematically prove it, and you have to double underline it. But the explanation here is that this is really the x component or parallel component. And that parallel component balances the 43.3. And that makes perfect sense, hopefully. All right, let's move on to the shear force. Again, I start with my unknown, so plus V of 5 on the right side, which is pointing downwards, therefore it's negative. And let me reiterate that this comes from here, so the black negative comes from here, whereas this positive comes from reading an arrow properly in a sketch. All right, now I bring in my 11.3, so 11.3 Newton, and that has also a sense, and that is by definition positive, but it's pointing upwards, therefore it's also positive. Now I need to indicate my 10 Newton here, so I have plus 10 Newton, but that 10 Newton is pointing down, therefore it's negative. And last but not least, I also have 50 times 50 times sine 30, so 50 sine 30, and that is positive, but it's pointing downwards, therefore negative here in my black identifier. And we can now state that this is the perpendicular component. And when I talk about these components, I mean relative to x-axis. Right? So it's relative to x-axis because that's where the reference fiber is, and that's what we need to always follow our logic. But I can solve this equation now, and I can find that my shear force V of 5 to the right now is really equal to, be careful now, it actually happens to be a negative value, and that value needs to be minus 23.57, minus 23.57 Newton. And we just leave it as a negative value because we're talking about internal forces, and later on we'd want to graph them. But for now, we understand that it's a negative value. And by the way, think about the difference between this shear force and the one that you calculated before. Where do you think that is coming from? I will give you the answer about that in a second. But before, let's find our last unknown here, which is the moment at 5 to the right, and that by definition is positive, but also it's rotating counterclockwise, therefore that is positive. Now I include my 11.3 Newton, and that is positive, of course, but it's also multiplied by 4 5 point something, so 5.00001. So multiplied by 5.0001 meters. And that now rotates again about this point. So this force rotates clockwise, therefore it's negative, which I need to indicate here. And I include my 10 Newton once again, 10 Newton, which is also positive, and multiply that by 1.0001 meter. And that is turning counterclockwise, if I'm not mistaken. Yeah, so I turn about this point, this force turns this way around, counterclockwise, therefore positive. And now, just to be sure here, or just so that you see it once properly, we can also say that we have the 50 Newton times the sine of 30, that gives us the perpendicular component, multiplied by 0.000001 meter. So we don't really care about this. In fact, this would be equal to 0, but if we were to include this, we would have to give it a rotational sense of, let's look at it, it would turn this way around counterclockwise, therefore positive. So plus 0, right? I mean, that makes no difference here for us, but we know now that we can calculate the moment m at 5 to the right would be equal to positive 47.15 plus 47.15 Newton meter. And that once again means positive tension on the bottom, compression on the top, or tension in the reference fiber, or smiling happy guy, right? So these are our results. Let's look at it in context. In fact, if I were you, I would now compare this page to the previous page and try to really understand what happens with the different forces. Before I talk about the whole context, let me just compare what we see on this page here. So here we had a negative force of 43.3, which really resulted from this force here. But if I compare this to the normal force down here, it goes to 0 from here to here. It becomes 0 because we now add this component, the parallel component. And again, if you think about it, this is really the component that causes the support reaction anyways, and therefore it's now in balance, and we don't need a normal force anymore to balance it. Now for the shear force, we started up here with 1.43, which if you go one page back, you will find that this is the same shear force that we had just to the right of this force. So that was 1.43 as well. But now if we look down here, it actually changed. And by how much did it change really from here to here? It changed by this amount, right? Because if you look at this equation, the only difference between this equation and this equation is really the 50 sine 30. So what you can really see is that from here to here, there's no difference because you have no force, but once you add this force, something changes, and that is reflected right here. Now look at the moment, 47.15 and 47.15, that did not change. That's really interesting, right? And that is because the moment rotates about a point. So it rotates about this point and this point. And if the points are not very far away from each other, in fact, they are not away from each other at all in a sense, but we just try to symbolize it by the 0.999999 versus the 1.100001, that they are somewhat far away from each other, but they are not far away from each other. They are very close to each other, and that's why this value is the same as this one. However, compared to the value on the previous page, you will find that you actually have a different value, and that they are so close to each other. Like here we have 47, on the previous page you have 45. That is completely random, right? So everywhere in between here, from here to here, you actually would find a different value. In fact, for you to practice, what I recommend is to probably find the internal forces at 4.5 meters, for example. That is something where we will pick up the next lecture, and we will actually find the internal forces almost everywhere along the entire beam. So you can practice that and prepare for that by calculating, for example, the internal forces at 4.5 and maybe at 2.2. It's something that you could easily do now with the knowledge that we presented to you here in this lecture, and I wish you good luck with that. One last word here before we conclude the lecture is, remember that this here is pretty much the left side of the system. We could also have released the other side, right? I could have created the system here where I cut the same part, but I now introduce actually only the force here, which is, I believe, 23.57, and then I cut right here where I will bring in now my internal forces, my shear force, my normal force, and my moment. And if I use those, then I would find the exact same answers. In fact, it's very easy to see here that this force here, this shear force, which, by the way, look, that is pointing up, whereas here is pointing down, right? This force, to balance this force, must be what? Minus 23. And look what we found here, minus 23.57. So that clarifies that this side is identical to that one. Why did I show you this? Because in an exam, after I really studied these problems in depth, I would definitely use this cut and not this cut if I were to solve the problem. But here, this was an educational example, so we tried to show you extensively why and how we calculate these numbers. Later on, when you're more proficient at it, and after you have some practice, hopefully you can find shortcuts. For example, cut the right side instead of the left side when you are asked to find internal forces at a specific location. But for now, I believe this concludes our first introduction to internal forces. We have seen how to calculate them for a simply supported beam that only carries concentrated forces. Later on, of course, we will include distributed forces, and we also will take it further to analyze the forces really everywhere along the beam. We will graph it later. But for now, I highly recommend that you explore this through your homework and really study how to find internal forces at a specific location so that you are ready to understand the following concepts, because we will really move fast forward from here on. And the topics will not become simpler, they will get more involved, and everything will rely on what we talked about today. But I believe this lecture is a very important one, hand in hand with the one where you learned how to calculate support reaction for a cantilever, because it's so similar to what we're doing here. And so if you understand those two lectures, you are very prepared for what's coming up. Just go ahead and solve the homework, but we will talk about this now after we concluded the lecture on the following page. Time to conclude the lecture, so please go ahead and fill out your takeaways and your muddy points so that we can better identify how to help you with this in the future lectures. What we definitely want to do together real quick is check our final checkpoints and talk about the conclusion of everything we touched upon in this lecture. So first of all, we talked about rigid bodies and how they are held together really by internal forces. And that is true anywhere along the axis of the rigid body. So hopefully we can agree on that. I believe we can both check it off. Then you understand that there are three forces really in a 2D system, and those are the normal forces, the shear forces, and the bending moment. And of course, we fully understand what those are now, at least conceptually. So I can check that off too, and you can go ahead and do the same. Then we talked about this thing of a virtual cut, right? So you understand that you can always virtually cut any rigid body at really any point. Of course, we did it at very specific points here, but the reason you do that is because you want to release the internal forces. And by doing that, you really turn them into external forces for which you already have all the mathematical knowledge to solve for such external forces. So the internal forces are really not calculated any different than the external forces. They just named differently, and after you cut them, you effectively have an external force that you then can solve for using the cantilever method. Then we are aware that we have a precise definition for each of these, right? So we don't randomly assign internal forces. We have a positive shear force, a positive normal force, and a positive moment. And they are very specific to their orientation, and that relates to the reference fiber. We obviously understand that because without the reference fiber, we could not properly assign them. So let's check that off. Then we need to understand that the positive internal forces always act in the same direction as the predefined ones, right? So this is something that was inherent to what we talked about. So the predefined is really what you have on your little study card. And if the value come out to be positive, then it goes in the same direction. If the value comes out to be negative, then it is actually opposite to that. However, you will never flip around the forces here. You will always keep them positive or negative, and that will become more clear as we go through further lectures. But for now, we understand that there's a predefined positive and a predefined negative. Now, what you also need to be able to do to solve these problems is to properly draw the free body diagrams that include all the known forces, and known forces are the external forces, including the support reactions, but you also need to bring in your three unknowns, the internal forces. And that is what really helps you to solve the problem, so we can shake that off too, because you understand that. And then last but not least, you understand that you can solve for internal forces by using the equilibrium equations or the conditions, because we understand that the unknown forces are really nothing different than the forces that act on a fixed support. So you can really use your knowledge from cantilever beams to find these internal forces, as long as all other forces, and that means external forces, on the subsystem are known. And I believe we can agree that this was definitely shown in this example or in this lecture, how you have to do that, at least for a simply supported beam. And of course, in future lectures, we're going to talk about more there. But for now, I think we can conclude the lecture, and we know now how to apply our knowledge. Of course, you can practice this more through your homework. So let's go ahead and decipher the homework on the next page. All right, let's discuss everybody's favorite page, the homework page, for which we usually end up with 6 problems. And here you have to find the answer to 6 problems for the internal forces at a specific location. Let's dive into the first problem, and let's see that we have a simply supported beam that carries 2 loads. These 2 loads are different from one another, although the system is geometrically symmetric, but you have to be careful because the load case is not. And what you're asked here is to find the internal forces N, V, and M at location C. So C is indicated here with that dot. And what that means is you have to find your support reactions first. And after you found the support reactions, you can either release the right side or the left side, bring in your internal forces, and solve for those internal forces. And there's really nothing more and nothing less to that. So we can move on to our next problem. So for problem B, it's very similar, except now you're actually dealing with distributed forces on top of that. And please don't get too confused about that. I see that sometimes in the classroom that students initially get confused, but all you have to do is cut through that force as well. So you either release the entire right system or the entire left system, and one of them might be easier for you than the other one, but I'm sure you can figure that out yourself. However, after you cut the system, either side, you just bring in your internal forces and you calculate them like you calculate cantilever support reactions, just by cutting through the system, even through the distributed force. So don't get too hung up on this. Again, I see that sometimes in the classroom, that initially students get hung up by the fact that the distributed force actually passes over the point, but just blindly cut it off on the other side, no matter if you do the right side or the left side. And I'm pretty sure you can solve this as well, because you already solved cantilever beams with distributed forces acting on them. Let's go to the next one. Now it becomes a little bit more interesting. We have actually triangular loads, but again, you also have calculated support reactions for cantilevers on triangular loaded systems. So here you look at something very similar. except now you find the internal forces at location C once again. And once again, you just release the system, either the right side or the left side. In this case, it really doesn't matter because it's truly symmetric. So it's really up to you. And you find N, V, and M as for all of these problems. So there's no real secret here that I can share with you. Of course, this can be challenging initially, depending on how well prepared you are. But I promise you, practice makes perfect in this case. And the more you practice here, the better it will become throughout the class. And you can see that everything in this class actually builds upon each other. And this is why you should definitely put a lot of effort into these homework assignments, because they will also lead you to the next step and to the following topics. Now, once again, a little bit more interesting here, we have a simply supported beam with overhang, and we have a distributed force here. And now you need to find the internal forces at that location. And so once again, you release the system, either the left side or the right side, and you bring in your internal forces and solve for them. So the trick here, similar to all the problems in this homework assignment, is really a strong sketch for your cut and then a standardized approach that I tried to exemplify to you in the lecture. So once you have that developed, I believe you can breeze through these problems with ease. So let's take a look at the last two problems. Now it becomes a little bit interesting because this is something we didn't cover in this class, internal forces for a cantilever beam. But to no surprise, it's no different after you found the support reactions. In fact, you may not even sometimes have to find the support reactions for cantilever beams, and this is something that you can learn through application as you solve these problems. Because remember, you have to release either the right side or the left side of the system. And so here one side requires you to find the support reactions first, the other one doesn't. And that is a little bit confusing as well. At least that's my experience in the classroom. And it was also confusing to me when I first started solving these problems. But again, practice makes perfect, and you just have to apply your knowledge more and more to really get proficient at these problems. And I promise you that every second and every minute you put into these problems really pays off at the end. And it definitely pays off in terms of your engineering understanding. So this is something we didn't practice in the lecture, but at the same time we did practice it because it's not really that different. And I let you explore that. Then we have a hinged beam here, which, yeah, this may look a little bit tricky compared to what we have done in the lecture, but at the end, it's always the same. You just release everything to the left side or to the right side of the location that you're looking for. In this case, we're looking for location D. So you cut the system here after you found your support reactions, and then you go ahead and solve for the internal forces at D. And that now concludes our lecture, and our homework is clearly defined now. I wish you good luck with that. Happy studying. I will see you in the next lecture. Until then, stay safe.